Hi there. In this video, we'll continue discussion about the statically indeterminate shafts and how to analyze them. The first one video we showed before, or went over before, is statically indeterminate shafts, but they are made up of composite sections. In this case, we're analyzing indeterminate shafts, but with unnecessary supports, or what we call also redundant supports. So we'll illustrate that by an example. So we have this shaft here fixed at A and C, same material, and with the load applied in almost the middle at point B. We are looking here for solving it and finding the reactions at the ends of the shaft at A and C. So if I jump right away into statics and free body diagram of the shaft here, I can see that the fixation at A and C will result in a reaction torques TA and TC. And if I pick my positive direction to be going, my axis will be going from the edge A, and using my right hand rule, thumb is going with the arrow, my hand is showing me the positive direction of this torque or moment around the axis. So when I do the sum of the torques, I will have here one equation and two unknowns. So TA plus TC will add up to the 300 Newton meters, but I don't know how much of 300 Newton meters goes to or supported by A and how much of it is supported by C. So like generally we learn we can solve statically indeterminate problems by either, in this case, the redundant support method. I can use it here, or the compatibility of deformations. So let's use the compatibility of deformations here. It's actually faster, and redundant force method is typically used just to introduce the idea of we having a redundant reaction. We can remove it, but we'll use here the deformation, compatibility of deformations or kinematics. So let's do the internal torque diagram so we can figure out what's the internal torque in each one of these segments I have and kind of figure out what's the deformation happening over the length of the shaft. So I'm drawing here the zero line of my diagram and I'm marking here ABC. My torque are in Newton meters. And I will start from the left in this diagram because my positive arrow that I picked before, I will stick to it. And it goes from the edge, out of the edge A. So that will be my positive direction. And to stick to it, I have to start from the left, from the face where this arrow is going out of. So I'm starting from A. And I have here TA is actually in the negative direction of the torque, so it's going down. So I'm dropping here with a negative value of negative TA. And I have a constant fixed value until I hit point B. And I will see here that 300 is positive value, so it will jump me by 300 Newton meter from negative TA so to 300 negative TA, which is actually from the statics equation. I know that also it equals to TC. So that keep going to the right fixed value until I hit TC. And TC here is a negative, it has a negative sign per my sign convention here. And that will drop me to equilibrium. So now I understand how the internal forces and equilibrium of that internally in that shaft look like. In the first part, AB, the torque is equal to TA. The second part, the torque is equal to C. So now I'm done with my internal diagram. I'm ready to analyze the deformations and make sure they are compatible. And compatibility of deformations here, if I say points A and C are fixed, so the rotation or twist of A relative to C or the other way is equal to 0. And I can break down this phi AC to be phi AB plus phi BC. And can detail more the formula for phi. So phi is equal to TL over JG. The whole shaft is made of the same material, so J is the same, G is the same, and it's the same diameter as seen here in the figure given to us. It's the same diameter and nothing changes, so it's the same J. So kind of I can cancel both of them next. But if we look at TA and TB, TAB and TBC from the diagram, it's the torque value between in segments AB and in segment BC. So this is actually TBC in the diagram. So I can see here these are the torque values that I will plug into my formula. So crossing J and G, and I will end up with TAB is actually negative TA, and TBC is TC. And this is my second formula that I can use to solve for two unknowns that I have. Use equation 1 and equation 2. Now I have a formula in just TA. Solving now for TA, that will give me 180 Newton meters. And when I solve for TC go back to either equation 1 or 2, I'll be able to figure out that TC is equal to 100 Newton meter. So we have seen that process over and over when we analyze the statically indeterminate axially loaded members, and now we're seeing a similar process when we analyze now this one is statically indeterminate shafts. You need to figure out from statics whatever equations you can find to relate the unknowns. If it's statically indeterminate, you will have less equations than unknowns. Figure out the deformations. Before you figure out the deformations, draw the internal force diagram for that type of force. So for us here, we're drawing for the torque. And then you move on to the deformations, compatibility, and conditions and constraints you have on deformations. Write it and figure out what's the deformation for values or formulas that you're going to use. And you will have your second equation or additional equations that will help you to solve for the unknowns. That's it. Thank you so much, and enjoy the rest of your day.